This module introduces the basic concepts of linear programming, its history, basic components, and its assumptions. It explains the concepts of formulating a linear programming problem with its economic applications. The main challenge faced by the business, industry, and governments nowadays is that various activities compete for limited resources. Hence, it becomes very much imperative for the decision maker to allocate these scarce resources in such a way that the optimum results are achieved. Linear programming, that is LP, is one of the best tools to achieve this objective. Linear programming problems help in allocation of scarce resources in the best possible way so that the costs are minimized or profits are maximized. It is a mathematical technique for optimum allocation of limited resources to several competing activities on the basis of a given criteria of optimality. Through linear programming, optimal solutions can be found to problems that use linear equations and inequalities. Linear programming is a generalization of linear algebra. It is the most widely used form of constraint optimization. Mathematical tools can be used to seek optimal solutions for business and economic problems, which can be converted into linear equations and inequalities. If one is able to convert real life problems into linear equations and inequalities of a linear program, the optimal, that is the best solution of the problem, can be found.
After starting this module, you shall be able to know the basic concepts of linear programming problems, its history, basic components and assumptions. You will also learn the concepts of formulating a linear programming problem with its economic applications. The main challenge faced by businesses, industries, and governments nowadays is that various activities compete for limited resources. Hence, it becomes very much essential for the decision maker to allocate these limited resources in such a way that he achieves the optimum results. Linear programming is one of the best tools to achieve this objective. Linear programming is a mathematical technique for optimum allocation of limited or scarce resource to several competing activities on the basis of a given criteria of optimality, so that the costs are minimized or profits are maximized.
Before understanding the concept of linear programming and its formulation, let us first consider different definitions proposed by different mathematicians. Linear programming can be defined as a mathematical method for determining a way to achieve the best outcome, such as the maximum profit or lowest cost in a given mathematical model for some list of requirements represented as linear relationships. Linear programming is a specific case of mathematical programming, that is, mathematical optimization. Linear programming can also be defined as a mathematical model to allocate scarce resources to competing activities in an optimal manner when the problem can be expressed using a linear objective function and linear inequality constraints. Linear programming may also be defined as mathematical technique to find the best possible solution in allocating limited resources such as energy, machines, materials, money, personnel, space, time, etc. to achieve maximum profit or minimum costs. However, it is applicable only when all other relationships are linear.
This mathematical technique helps in finding optimal solutions to problems that can be expressed using linear equations and inequalities. A linear function, when drawn on a graph, forms a straight line and has the following form. In the equation, a's are called the coefficients of equation or parameters. Coefficients are fixed values which depend primarily upon the problem concerned. The x's are variables in the equation. These variables take range of values, and range is primarily defined by the constraints. Let us understand the components of linear programming problems. These are objective function, constraints, variables, and non-negative restrictions.
Thus, a general linear programming problem consists of objective function, constraints, variables, and non-negativity restrictions as mentioned earlier. Objective function. The objective of a linear programming problem will be to maximize or to minimize. The objective function describes the contribution of each variable to the value to be optimized. The objective function takes the following general form of maximizing or minimizing a given function. The coefficients of the objective functions indicate the contribution to the value of the objective function of one unit of the corresponding variables. Of course, some variables may not contribute to the objective function at all. In this case, you can either think of the variable as having a coefficient of 0, or you can think of the variable as not being in the objective function at all. Decision variables are the most commonly known variables. Variables generally denote those factors which can be adjusted or controlled to optimize given problem. The objective of the linear programming is to find out the value of decision variables in such a way that it either maximizes or minimizes the value of the objective function. Typically, the variables represent the amount of a resource to use or the level of some activity. Generally, a variety of symbols with subscripts and superscripts are used to represent the variables of a linear programming. For example, capital X1, X2, Xn could be used when there are n variables in the list. Constraints are a set of mathematical equalities or inequalities which combine the decision variables to put limit on the optimal solution. These define the possible values that the variables of a linear programming problem may take. Constraints generally represent minimum or maximum level of some activity or condition. For example, the availability of raw materials, the availability of laborers' time, etc. are good examples of constraints. The right-hand side of the constraint indicates the total amount of resource available for the project, whereas the left-hand side of the constraint signifies the restriction. Constraints generally carry less than or equal to or greater than or equal to and equal sign, and sometimes are unrestricted. A greater than or equal constraint can always be converted into a less than or equal constraint by multiplying it by -1. Similarly, equality constraints can be written as two inequalities, a less than or equal constant and a greater than or equal constant. Non-negativity restrictions state that decision variables can take any value between 0 to infinity. That is, the decision variables are restricted from taking any negative values. It provides bounds to the decision variables. In some cases, where user actually wants a negative value for the variable, there are certain formulation tricks that can be employed. In any case, the non-negativity constraints are part of linear programming formulations, and you should always include them in a linear programming formulation. We will discuss all these components of linear programming functions one by one.
Let us first discuss objective function. The objective of a linear programming problem will be to maximize or to minimize the concerned variable. The objective function describes the contribution of each variable to the value to be optimized. It can be written as maximize or minimize z, which equals summation of I, where I ranges from 1 to n. Ci, where Ci is the coefficient of the objective function, indicates the contribution to the value of the objective function to the ith variable, and Xi is the decision variable. Of course, some variables may not contribute to the objective function at all. In this case, you can either think of the variable as having a coefficient of 0, or you can think of the variable as not being in the objective function at all. Decision variables are most commonly known as variables. Variables generally denote those things which can be adjusted or controlled to optimize the given problem. The objective of the linear programming is to find out the value of decision variables in such a way that it either maximizes or minimizes the value of the objective function. Typically, the variables represent the amount of a resource to use or the level of some activity. Generally, a variety of symbols with subscripts and superscripts are used to represent the variables of a linear programming. For example, x1, x2, and so on till xn could be used when there are n variables in the list. Constraints are a set of mathematical equalities or inequalities which combine the decision variables to put a limit on the optimal solution. These define the possible values that the variable of a linear programming problem may take. Constraints generally represent minimum or maximum level of some activity or condition. For example, availability of raw material, availability of laborers' time, etc. The right-hand side of the constraint indicates the total amount of resource available for the project, whereas the left-hand side of the constraint signifies the restriction. Constraints generally carry less than or equal to, more than or equal to, and equal to sign, and sometimes are unrestricted. Non-negativity restriction states that decision variables can take any value between 0 and infinity. That is, decision variables are restricted from taking any negative value. It provides bounds to the decision variables and can be written as, say, non-negative restriction is on xi. It can be written as xi greater than equal to 0, where I ranges from 1 to n. This inequality implies that x can take any value equal to and greater than 0. Therefore, it cannot take any negative values.
Now we will discuss the assumption on which linear programming model is based. Some assumptions are related to appropriateness of the formulation, while some assumptions are related with the mathematical relationships within the model. We assume that proportionality exists between objective function and constants, that is the contribution of each activity, say x1 to the value of objective function are proportional to the activity itself. By proportionality, we entail that the difficulty which is to be studied through linear programming must be devised in the form of linear functions of two or more variables which are also subject to a group of linear restraints, at least one of which must be articulated as inequality. That means one can find out a common factor k between the contribution of each activity to the value of the objective function. The assumption of additivity states that objective function as well as left hand side of a constraint in a linear model is equal to the sum of individual contributions of that activity. That means finite and definite relationship exists between decision variables, or to put it in different words, there can be no interactions between the effects of different activities. That is, the level of activity x1 should not affect the costs and benefits associated with the level of activity x2. Divisibility assumption implies that decision variables in a linear programming model can have integer as well as non-integer values. The underlying assumption is that activities can be performed at fractional levels. Sometimes these values only make sense if they are integers. Then we need an extension of linear programming called integer programming. As per certainty assumption, every parameter carries a known and constant value, which can be ascertained with most certainty. In other words, the model assumes that the responses to the values of the variables are exactly equal to the responses represented by the coefficients. In real life situations, however, certainty assumption does not always hold good, since model parameters reflect present as well as future variables, which brings in the uncertainty factor into the model.
Let us discuss the assumptions on which this technique is based. The first assumption is proportionality. In this, we assume that proportionality exists between objective function and constraints. This means that one can find out a common factor k between contributions of each activity to the value of objective function. For example, in this figure, the red line violates the proportionality assumption since the line is not straight or linear, whereas the blue line satisfies the proportionality assumption as the line is straight, or one can find the common factor between contributions of each activity to the value of objective function at any level. Additivity. This assumption states that objective function as well as left-hand side of a constraint in a linear programming model is equal to the sum of individual contributions of that activity. This means that finite and definite relationship exists among decision variables. That is, the level of activity x1 should not affect costs or benefits associated with the level of activity x2. Divisibility. Divisibility assumption implies that decision variables in a linear programming model can have integer as well as non-integer values. The underlying assumption is that activities can be performed at fractional levels. Sometimes these values only make sense if they are integers. Then we need an extension of linear programming called integer programming. Certainty. As per certainty assumption, every parameter carries a known and constant value, which can be ascertained with utmost certainty. In other words, the model assumes that the responses to the values of the variables are exactly equal to the responses represented by the coefficients. Data. Formulating a linear program to solve a problem assumes that data are available to specify the problem. Let's consider a linear programming problem having n decision variables, that is, x1, x2, and so on till xn. The standard format of a general linear programming problem may be written in the following format. The objective function is to maximize or minimize z, which equals c1x1 plus c2x2 and so on till cnxn, subject to constraints. In this equation, c1, c2 and so on till cn are called cost coefficients. AIR are called substitution coefficients. B1, B2 till Bm represent availability or requirements of M constraints. The non-negativity restriction implies that xj's must be non-negative.
Mathematical formulation is the most important part of linear programming problem. Mathematical formulation of linear programming problem, that is LPP, means converting descriptive given problem into mathematical form in terms of objective function, constraints and non-negativity restrictions. Generally, these steps followed in this process are: first, identify decision variable. Second, write down the objective function. Third, write down the constant. Fourth, write down the non-negativity restriction. Now we will discuss these steps one by one.
Mathematical formulation of linear programming problem means converting descriptive given problem into mathematical form. The steps involved in this process are as follows. Identify decision variables. Identify the decision variables whose value is supposed to be determined by following one basic principle into the mind. That is, the problem is of maximization, then variables denoting profit, revenue, etc. should be assumed as decision variable. And if the problem is of minimization, then variables denoting cost or loss, etc. should be taken as decision variables. Write down the objective function. Identify the type of optimization, that is, maximization or minimization. Linearity assumptions should be invoked to write the objective function. While writing the objective function, we are also assuming constant returns to scale. Write down the constraints. Identify the constraints expressed in terms of decision variables with appropriate equality or inequality. Write down the non-negativity restriction. Add the non-negativity restriction of the decision variables. Non-negative restrictions mean that all decision variables must be 0 or more than 0.
These steps will become clearer from the following example. A machine tool company conducts a job training program for machinists. Trained machinists are used as teachers in the program at a ratio of 1 for every 10 trainees. The training program lasts for 1 month. From past experience, it has been found that out of 10 trainees hired, only 7 people complete the program successfully. The unsuccessful trainees are released. Trained machinists are also needed for machining, and the company's requirements for the next 3 months are as follows: January 100, February 150 machinists, and March 200 machinists. In addition, the company requires 250 trained machinists by April. There are 130 trained machinists available at the beginning of the year. Payroll costs per month are as follows: each trainee is paid rupees 400, each trained machinist, that is machining or teaching, he is paid rupees 700, each trained machinist idle, as the union forbids firing them, he is paid rupees 500. Now we can set up the linear programming problem that will produce the minimum cost hiring and training schedule and meet the company's requirements. Let us now solve this linear programming problem. Each trained machinist can either work on the machine, or he can teach, or he can stay idle. The number of trained machinists is fixed. Therefore, the decision variables are the number teaching each month and the number idle each month. Let us presume that x1 is equal to the number of trained machinists teaching in January. x2 is the number of trained machinists idle in January. x3 is equal to the number of trained machinists teaching in February. x4 is the number of trained machinists idle in February. x5 the number of trained machinists teaching in March, and x6 the number of trained machinists idle in March. Each month the total number of trained machinists is equal to the number machining plus the number teaching and plus the number who are sitting idle. So therefore January is equal to 100 plus x1 plus x2, which is equal to 130. That implies x1 plus x2 is equal to 30. Now in the month of February, it is 150 plus x3 plus x4 is equal to 130 plus 7x means 7x1. That implies 7x1 minus x3 minus x4 is equal to 20. Note that each machinist teaching trains 10 with 70% success. In the month of March, 200 plus x1 plus x6 is equal to 130 plus 7x1 plus 7x3, which gives us 7x1 plus 7x3 minus x5 minus x6 is equal to 70. Therefore, in the month of April, 250 trained machinists required in April. The equation would be 130 plus 7x1 plus 7x3 plus 7x5 is equal to 250, which gives us 7x1 plus 7x3 plus 7x5 is equal to 120. The cost of machinists operating is constant and therefore not required in the objective function. Relevant costs are: 1. The cost of training program, that is the cost of trainees plus the cost of the teachers. 2. The cost of idle machinists. The objective function is to minimize the cost, that is minimize Z equal to 400 into 10x1 plus 10x3 plus 10x5, which is the cost of the trainees, plus 700 into x1, x3 and x5, that is the cost of the teachers, plus 500 into x2 plus x4 plus x6, that is the cost of the idle machinists. Thus the problem is to minimize Z equal to 4700 x1 plus 500 x2 plus 4700 x3 plus 500 x4 plus 4700x5 plus 500x6, subject to x1 plus x2 is equal to 30, 7x1 minus x3 minus x4 is equal to 20, 7x1 plus 7x3 minus x5 minus x6 is equal to 70, 7x1 plus 7x3 plus 7x5 is equal to 120 with the conditions x1, x2, x3, x4, x5, x6 greater than or equal to 0.
In this module, we have learnt about the formulation of linear programming problem. Linear programming is a specific case of mathematical programming or mathematical optimization. A general linear programming problem consists of objective function, constraints, variables, and non-negativity restriction. We also learnt the assumptions on which linear programming is based and its mathematical formulation, that is, how it converts descriptive given problem into mathematical form in terms of objective function, constraints, and non-negativity restriction.